Let's add a couple of tools to our toolbox. At this point, we can identify geometric and telescoping series, and we have a means to not only determine if they converge or diverge, but also to actually sum them. In addition, we've learned the divergence test, the integral test, and p-series to examine whether or not a series converges or diverges. In section 9.5a, we will learn two comparison tests. Now, in general, it's not a good thing to compare yourself to others unless you are a series. That can be tremendously helpful. In this video, we will examine the direct comparison test. Here's the theorem. Let a sub k and b sub k be series with positive terms. Later on, we'll examine what do we do if we have some alternating positive and negative terms in there. So we have two infinite series that we're going to be comparing. If both of our series are positive, that is, they're both bigger than 0, and a sub k is less than or equal to b sub k, this is term by term for each increment of that index k, and we know that the series b sub k converges. Okay, now check this out. If the series b sub k converges, and term by term, the other series is less than the terms of this bigger series, well, the convergence of this one is going to require that the one that's less than it also converges. Thus, we can say the series a sub k converges. So if the series that you're examining is smaller term by term than a convergent series, then the series in question converges. And remember, converges simply means that it has a finite sum. Number 2, if 0 is less than b sub k less than or equal to a sub k and b sub k diverges, so this guy is going to diverge, and it is term by term smaller than the terms of the series that we're examining. Well, when this one explodes or diverges to infinity, it's going to push this one up as well. Therefore, the series a sub k diverges. That means that as we add the terms indefinitely, the sum continues to get larger and larger and doesn't settle down on a finite value. The hard part about the direct comparison test is that sometimes you have to be a little bit creative. You have to determine a series that you know the behavior of to compare the one that you are questioning. Let's try this in example 1. Use the direct comparison test to determine if the following series converge or diverge. So we have the sum from k equals 1 to infinity of 1 over 3k squared plus 2. Now, just for a minute, if that plus 2 were not there, if I could just cover it up and not think about it, then this would be similar to a p-series. We could compare this to the sum from k equals 1 to infinity of 1 over 3k squared. Okay, so the little squiggle here simply means the series are similar or comparable. Now, this is a good comparison because we know the type of series we're dealing with. This is a p-series. P is equal to 2. Since p is greater than 1, we have a convergent p-series. So the series we're questioning is similar to a known series that converges. So if we're dealing with a convergent series, it would be convenient if we could show that the one we're trying to examine is term by term less than our convergent example here. So let's find out if that is true. The series we are examining is 1 over 3k squared plus 2, and we want to find out, I'm going to put a little question mark up here, is it less than or equal to the series 1 over 3k squared? Now notice because k starts at 1 and goes to infinity, all of these values are positive. That means I can go ahead and cross multiply here without having to worry about reversing my inequality sign. So we have 3k squared less than or equal to 3k squared plus 2. Now, if I look at this inequality, I could very easily observe that this is true for all k, and in particular greater than or equal to 1 since our series starts at 1. 3k squared is going to be less than or equal to that same item plus 2. You could also verify this a little bit further. If you wanted to subtract 3k squared from both sides, you'd end up with a statement that is always true. Since the series in question is term by term smaller than a convergent p-series, then the series we're examining converges. So let's make our conclusion by direct comparison to the convergent p-series the series sum from k equals 1 to infinity of 1 over 3k squared plus 2 converges. So notice we have cited the test that we're using here, direct comparison, and we have also added the detail that the series we're comparing it to converges because it is a p-series. So that's another authority we're citing here. So we can make our conclusion this series converges. Let's try another example. We have the sum from n equals 1 to infinity of 1 over 4 cube root of n minus 1. Now, if the minus 1 were not there, we could say this is very similar to the sum from n equals 1 to infinity of 1 over 4 n to the 1/3. I'm going to rewrite that cube root of n as n to the 1/3. The reason is so that we can identify that this is a p-series. The p-value is 1/3, which is less than 1. So this is a divergent p-series. Since this one is divergent and we're attempting to compare it to the given series, we want to show that the known series is smaller than the given series. Remember, if your series is bigger than a divergent series, it also must diverge. So I want to find out, is 1 over 4n to the 1/3 less than or equal to 1 over 4? I'm going to write that as n to the 1/3 minus 1. And again, we're attempting to establish this. So multiplying both sides, or cross multiplying here, which is definitely legal because we're dealing with positive numbers, we have 4n to the 1/3 minus 1 less than or equal to 4n to the 1/3. This is obviously true for all n, and in particular greater than or equal to 1. Because if I have a number subtracting 1, it's going to be bigger than that number. But if we wanted to go ahead and prove it beyond the shadow of a doubt, we would simply subtract 4n to the 1/3 from both sides, and we end up with a statement that is always true. So we can say by direct comparison to a divergent p-series, the given series sum from n equals 1 to infinity of 1 over 4 times the cube root of n minus 1 also diverges. Now that is the conclusion statement. It's really important that I have this in my body of work to establish the hypothesis. The hypothesis is that our known series is smaller than, term by term, the given series. Since our known series diverges, it causes the bigger one to also diverge. Now, direct comparison can be challenging. It can also be very useful. Let's look at example C. The sum from n equals 1 to infinity of 4 to the n over 5 to the n minus 3. Now, I notice a common power of n in the numerator and the denominator. So this is similar to the sum from n equals 1 to infinity of 4 to the nth power over 5 to the nth power, which, if I rewrite it like this, you may recognize as a geometric series, because the common ratio r is less than 1, r, which is 4/5, less than 1. This is a convergent geometric series. Because we're recognizing a similarity with a convergent geometric series, we would need to show that the series in question is term by term less than or equal to this geometric series. If we can get our series in question smaller than a convergent series, then our conclusion would also be convergence. So because we're dealing with all positive terms here, again, I'm going to cross multiply. So I have 4 to the nth times 5 to the nth is less than or equal to 4 to the nth times 5 to the nth minus 3. Now, I should be careful as we're exploring this option. We're trying to establish, is this a true inequality? And we've whittled it down to this last line. So what we know here is that 4 to the nth is the same on either side. So that's not going to affect the inequality. We could certainly divide both sides by 4 to the nth and cancel it out. But if I compare these two terms, 5 to the nth is bigger than 5 to the nth minus 3, right? A number is bigger than a number minus 3. So this is not a true inequality. So the direct comparison test for this particular case is not helpful at all. I don't know if it converges or diverges. So I could begin working back through the other tools in the toolbox. How else can we determine if this converges or diverges? Although it's similar to a geometric series, it is not a geometric series. It is also not a telescoping series. So we can rule out those two tools. If we wanted to apply the divergence test, if we take a limit of the term of the series as n goes to infinity, the limit is going to be 0. So our divergence test would be inconclusive. This is also not a p-series, so that is not a possibility. And I don't know about you, but I don't want to have to figure out a way to integrate that. So right now, all of our tools are not a good fit. So we do see there's a need for another possibility. The next test that we're going to study is called the limit comparison test, and it's going to be most useful for this particular one. So we'll say, to be continued, and I'll give you a hint. Here's your cliffhanger. Try limit comparison. So we've done direct comparison. In the next video, we'll learn about limit comparison test.